Hello and Assalamualaikum everyone. So this week we're going to move on to our final queuing model under lecture 3, which is the unlimited service queue Infinity queue. Okay, so but before that we're going to have a look at the probability distribution of waiting time for MM1 and MMC model. Okay, so previously we have learned the distribution of a waiting time, okay, for new arrival with mean of n over mu and standard deviation of square root n over mu when you have n customer in the system. Okay, so based on the value of the mean and standard deviation, so the distribution of waiting time actually follows a gamma distribution with the following parameter. Okay, so in this section we will show the derivation of the distribution of waiting time. So the first one is the waiting time in the system, which we're going to denote with the symbol of W, curly W, okay, and the waiting time in Q, which basically the waiting time in system minus the time in service, which we're going to denote with the symbol of our curly W, Q. Okay, so the type of distribution is basically a gamma distribution, which is a convolution of multiple exponential distribution. So in queuing theory, the distribution is also known as the Erlang distribution, which is a special type of gamma distribution. Okay, so basically the difference is that, okay, so previously we have learned the value of expected waiting time in system, which is our W, and expected waiting time in the Q, which is our WQ. So this value is actually the mean of the one that we're going to derive in this section. Okay, so for MM1 queuing model, we're going to assume that our lambda is less than mu. Okay, the Q discipline is on a first in, first out. So first we want to derive the probability distribution of waiting time in the system, okay, which is our W here. So this is the waiting time in the system. Okay, so first let us recap. Okay, so basically you have a new arrival. So this new arrival arrive. Okay, so it will get a service, and after getting service, your customer will depart. Okay, so here is the time, okay, where the customer wait in queue. Okay, so here is the time where the customer basically in the system. So wait in queue plus the time receiving the service. So this is what we're going to have a look at. So this is our WQ, the curly WQ, and this is our curly W. Okay, so if your arrivals finds that there are already I customer in the system, so you have a new arrival, so you already have I customer in the system, so the arrival basically have to wait for I plus 1 exponential service time including its own. So this new arrival will get the service here, okay, because you have one server. This is for MM1Q. Okay, so it has to wait for I plus 1 exponential service time here, okay, including its own before it can depart the system. Okay, so first let us define, okay, so T1, T2, okay, and so on, be the independent service time random variables having exponential distribution with parameter mu. Okay, so and then we're going to let our S I plus 1 be the conditional waiting time given that I customer are already in the system. Okay, for your I equals to 1, 2, and so on. Okay, So since the probability that the random arrival will find I customer in the system is pi I, okay, so it follows that, okay, the probability that the waiting time is greater than time t equals to the summation of I equals to 0 until infinity pi I times the probability, okay, of the conditional waiting time given there are already I customer in the system. Okay, so these equations, okay, subsequently will be reduced to, okay, give you this value, okay, of waiting time greater than certain time t equals to e to the power of negative mu 1 minus rho t for your time t greater equals to 0. Okay, so the reduction part is not included in our course, but it is provided in your lecture notes in case you want to know how, okay, this equation reduces to this. Okay, so basically the distribution of your waiting time in the system here follows an exponential distribution with parameter of mu times 1 minus rho. Okay, so this basically can show us, okay, that the expected waiting time in system that we derived earlier, okay, is actually the mean of your waiting time equals to 1 over mu 1 minus rho. Okay, so remember, since this is the result of waiting time in the system, it also includes the service time and the waiting time altogether. Okay, so it includes this, okay, all of this. Oh, sorry, not that part. Okay, so it includes this, okay, so waiting time in the system. Okay, but often or somehow, if let's say you're just interested, okay, in this part, okay, waiting time in queue before you get the service, okay, right? So the waiting time in queue excluding the service time, okay, where we're going to denote with this symbol, okay, for a random variable based on first in first out basis. So if your new arrival finds no customer in the system, then the arrival is served immediately. Okay, so the probability of the customer not having to wait, where your waiting time is equals to 0, is equals to the probability of the system being in state 0, which is your pi node. Okay, because the customer will only get immediately served when there are no customer in the system. So it is equals to the probability of your system being in state 0, which is pi node, which is equals to 1 minus rho. This is the probability of having no waiting time. Okay, so if the customer or the new arrival finds I customer in the system, okay, let's say your I is greater than 0, okay, then the arrival has to wait for I exponential service time. Okay, greater than t, so we will have the summation from I equals to 1, okay, because when the state of the system is greater or equals to 1, then only the customer have to wait. Okay, so the probability of the conditional waiting time, okay, greater than t, okay, when there are already I customer in the system greater than t. Okay, recall that your pi I for mm1 is 1 minus rho to the power of I. Okay, so here you will have I equals to 1 infinity 1 minus rho to the power of I. So probability of there are I customer in the system. Okay, so let us factor out our rho. Okay, so we will have 1 minus rho to the power of I minus 1 as I greater than t. Okay, which by rephrasing I equals to 0, we will get 1 minus rho to the power of I, probability of S, I plus 1 greater than T. Okay, so this is actually equals to pi I greater than T. Okay, so which is equals to the probability of your waiting time greater than time T. So you will have rho times e to the power of negative mu 1 minus rho T for your T greater equals 0. Okay, so that is the value of your probability of waiting in the queue for more than T. Okay, so for this WQ, okay, it does not have an exponential distribution. Okay, you cannot say that your WQ is equals to the follows the exponential distribution. Okay, however, the conditional distribution of this waiting time, okay, given that your waiting time is greater than 0, does have an exponential distribution. Okay, so the conditional probability that the waiting time is greater than time t, given that the waiting time is greater than 0, okay, is actually equals to W greater than T, and then your waiting time greater than 0, which will gives you e to the power of negative mu 1 minus rho T for T greater equals to 0. Okay, so this conditional probability follows an exponential distribution with parameter of mu 1 minus rho. Okay, so by deriving the mean of the unconditional distribution of waiting time in Q, okay, so by using Little's formula, okay, so that's okay, so then we will get our expected waiting time in the system, or WQ, okay, is equals to the expected waiting time, okay, or the average waiting time in the queue, which is equals to lambda over mu times mu minus lambda, as we have derived earlier. Okay, and then for MMCQ, okay, there is no proving, okay, that we're going to show, so you can just refer to your lecture note, okay, for the value or the formula for MMCQ for probability of having to wait, probability of the waiting time greater than T, and also probability of the waiting time in Q greater than T. So this is provided in your lecture note. Okay, you can just refer to the formula, so when the question asks you, you can just substitute the value of all of the parameter to get the answer. Okay, so now we're going to move on to our final queuing model. Okay, so which is our unlimited service queue infinity. Okay, so this is the transition diagram for our infinity queue, because now we would like to treat, okay, our queuing model where we have an unlimited service or server. Okay, so we have infinite number of server available. Okay, so a self-service situation is a good example of such model. Okay, so we're going to make use of the general birth-death process, okay, where we have our lambda I, arrival rate equals to lambda for all of our I, and then we will have our service rate mu I equals to I mu for all I, depending on the current state in the system. Okay, so now, okay, based on our knowledge from our birth and death process. So we will have, okay, the probability that the system in state I is given by pi I equals to lambda to the power of I over I factorial mu I times pi naught, okay, for your I equals to 1, 2, and so on, okay. So the value of your pi naught here, okay, based on the one that we have learned previously, okay, the summation of I equals to 0 until infinity, or lambda I over I factorial mu I, okay, to the power of negative 1. Okay, so next what we're going to do is we're going to determine the value of pi naught, okay. So the infinite series of pi naught is actually equals to e to the power of r, where your r is equals to lambda over mu. Okay, so you have your pi naught equals to lambda to the power of I over I factorial times mu to the power of I, okay, to the power of negative 1. If you were to expand, you will get 1 plus lambda over mu plus lambda square over 2 mu square plus lambda cube over 3 mu cube, and so on, which is equals to e to the power of lambda over mu. Okay, so that is why we get e to the power of r here. Okay, so since this is, okay, to the power of negative 1, okay, so we will get the value is equals to e to the power of negative r, where r equals to lambda over mu. Okay, so therefore we have our pi I for infinity q is equals to r to the power of I times e to the power of negative r for over I factorial, okay, for your I equals to 1, 2, and so on. Okay, so basically the value of lambda over mu or r is not restricted in any way, because, okay, anytime a new customer arrive, it will get served immediately because the number of server is unlimited. Okay, so the expected system size, okay, which is your L, okay, the expected of number of customer in the system is equals to your R, which is lambda over mu, okay, and your waiting time, expected number of customer waiting, and also your waiting time in queue is equals to 0 because the customer don't have to wait to get the service, okay, and the average time in the system, which is your W, okay, is equals to 1 over mu, which is basically just the time you get served, because you enter the system and then you will get served immediately without having to wait. Okay, so these are the measure of effectiveness for infinity. So you have your L, okay, equals to lambda over mu, your LQ equals to WQ equals to 0. Okay, sorry, this is not your curly W, it's your expected waiting time in queue. Okay, and then this is your expected waiting time in the system, which is just the time that you receive a service, the average time that you receive a service. Okay, so let us look at an example. Okay, so you have a television station known as channel 001. So this television station wishes to know the average number of viewers that it can expect on Sunday night primetime movie program. Okay, so it is found that people turning on their television sets, okay, people who watches TV on Sunday night is believed to follow a Poisson distribution with a mean of 100,000 person per hour. okay, person or 100,000 tuning in per hour. Okay, so it is believed that a given person or probably the household that will choose among 5 available TV stations, okay, that have the same type of program, which is the movie program on Sunday night. Okay, so surveys have also shown that average person or household, okay, will tune in for 90 minutes, okay, and the viewing times are approximately exponentially distributed. Okay, so the channel 001 wishes to know the average number of viewers it can expect. So first let us determine our lambda, and then we will determine our mu, and then we will find out our L. Okay, so for our lambda, okay, so 100,000 customer per hour will choose from 5 channels, so we will have 20,000 customer per hour. So that is our lambda. Okay, and for our mu, okay, so the average tuning time, so 90 minutes, which is equals to 1.5 hour. Okay, and then the number of viewer will just take the value of lambda over mu, which will give you 1.5 hour. Okay, so which will give you average 30,000 people will tune in to channel 001. Okay, so this is the answer, right? So that is it for lecture 3 and on week 5. Okay, so thank you very much.